Hello friends, today I'm going to talk to you about the reason why stress singularity occurs in a tension bar. This is a topic which I have seen is not very commonly known to even many CA engineers. That is one of the uh, important reasons why I have decided to make this video. So that is a mathematical topic, so a mathematical treatment can be extremely boring and complicated and a little bit difficult for novices and beginners. So I have tried to explain this here qualitatively without using mathematics. So these are the following assumptions made in this analysis. Linear stress analysis is valid. The material is linear, elastic, homogeneous, and isotropic. Then the continuum hypothesis is valid. These are the usual assumptions that we make in strength of material calculations. Here I'm adapting it for this analysis. So the main principle I'm going to use to explain this will be the principle of superposition. According to the principle of superposition, the response of simultaneous application of two loads, let us say A and B, will be equal to the sum of their individual responses. Also, this also means that the order in which we apply the loads doesn't matter as long as both the loads are active at the same time. We also have to note that this is valid only for linear analysis. For nonlinear systems, this is not always valid. Now, let me give you a visual example. Let us say there is a bar that is fixed at one end, basically behaving like a cantilever uh, with with a transverse load F and a tension load T acting on it. Now, the response will be the same whether we apply tension load and then retain the tension load and also apply the transverse load, or first we apply the transverse load and then we retain the transverse load and apply the tension load. So either way, the order in which the loads are introduced does not matter. And also uh, in this one, uh, if we apply the two loads separately, first let us say we apply the load F and then remove it and note the response and remove the F load. Then we apply the load T, note the response and remove the load. If you sum up the two responses, it will be exactly equal to the response of the system where F and T are acting simultaneously. So this is the basic idea of principle of superposition. So this idea I am going to use to explain the phenomenon of stress singularity. So here is a case study. There is a bar of these dimensions having this tension load. So these are the analytical calculations. So load by area. So the stress comes to 100 megapascals. However, when you do the finite element analysis for this using plane stress elements, we will discover that other two regions shown in on the screen with red dots, the stress does not converge. As you go on refining the mesh, the stress tends towards infinity. So as you can see from the regression analysis, uh, so as the stress, if we take a regression curve and we extrapolate the uh, the stress value at element size 0, it will be infinity. So this is called stress singularity in the literature, and this is a well-known stress singularity. So now the question arises, why does this singularity occur? In order to do that, I will take a simple plane stress 2D evaluation to show this. Now, on the leftmost, we have the diagram. We have a loading diagram, and it shows both the deformed and the undeformed shape. The deformed shape is shown by solid lines. Sorry, the undeformed shape is shown by solid lines, and the deformed shape is shown by the dotted lines. On the leftmost, that is in the figure that I'm explaining, the bar is fixed at one end and tension is applied at the other end. However, we will get exactly the same results if we apply a frictionless support at the bottom edge and along with the tension load, and later we we hold the bottom corners and pull them towards the undeformed position. So that way also we'll get the same shape. As you can see, the leftmost uh, diagram and the rightmost diagram are the same. So either way you get the same. So if the displacement field is exactly the same, the stress field will also be exactly the same. So what we realize here is that, so we are letting it, we can first let it stretch, that is go into tension without without constraining the lateral contraction, and the lateral contraction takes place freely. After that, we take hold of the two ends, two bottom corners of the deformed body, and we pull as shown by the red arrows towards the undeformed position, and then we bring it to the undeformed position, only the bottom two corners. So this gives exactly the same shape as when the structure is subjected to fixed at one end and load applied at the other end. So what is the explanation? As you can see, uh, what happens here is that all the load. So we are actually basically applying a point load on a continuous body. So this will lead to infinite stress, as the point load is a finite load that is acting on a zero area. So the stress becomes infinity. This is the reason why the stress singularity is there in this model. Why is the And now an important question arises. How can I say that this point load that I have applied to get the same displacement field is the only way? There is a reason for that. In this example, the horizontal displacements, when we don't constrain the lateral uh, contraction due to Poisson's ratio, it it creates a displacement field, a field of horizontal displacements that vary linearly along the bottom edge. Now, since we are not allowing the bottom edge to move because we have fixed it, so we have to exactly undo this. For that, we have to apply an opposing displacement field of displacements that varies linearly between the two bottom corners, just as it was varying linearly between the two bottom corners uh, before. So, and we have to apply the displacement in the opposite direction, in the same distribution in the opposite direction. So, and this is possible only when the two point loads act at the corners. So this is my way of justifying the uniqueness of this solution. So implications. So there are some implications about this. All the force that is caused by resisting the lateral contraction due to Poisson's ratio in this case has to be borne by an infinitesimally small area at the two bottom corners. So this means that a finite load is going to act on an infinitesimal area, giving rise to infinite stress. Now, even if we reduce the load a little bit, still it's going to be a smaller finite load acting on a zero area. Still, it will be infinity only. So this means that even if the slightest of loads acts, the stress will still be infinity. However, this does not mean that it will fail at very small loads because of fracture mechanics considerations. So it will fail only when the load is big enough to satisfy the energy requirements for the crack propagation, for the crack spreading. Uh, there is an interesting thing to note here. So there is we are resisting the lateral contraction. Because of that, these infinite stresses are coming. However, if you set the Poisson's ratio to zero, there will be no lateral contraction at all. In such a case, this singularity will not be there. This has been confirmed by literature. I conclude by saying that the stress singularity in this case is caused by the way the displacements are distributed in a tension bar fixed at the other end. Thank you, friends.